We have got 1 mole of this. Let's see if this is a limiting reactant. Two mole requires 6. So 1 mole will require 3 times, isn't it? 2 into 3 is 6. And oxygen is 3 by 2 times. 3 by 2 is 1.5. 3 moles are required, but present are only 2 moles. So 1 mole Fe2S3 is not going to work. It requires 3 moles of water, and we have got only 2 moles of water. But it requires 1.5 moles of oxygen, and we have got 3 moles of oxygen, more than what is required. So I think looking at these numbers, water should be the problem, limiting reactant. We want to know who is the limiting reactant and how much of FeOH thrice will be obtained. Water looks like as a limiting reactant. Suppose whole 2 moles of water are to be consumed. Then how much Fe2S3 you need? 2 by 6 times water. 2 by 6 times water is 2. That means you need 2 by 3. You need 2 by 3 moles. You have got 1 mole which is more than 2 by 3. No problem. And 2 moles of water require how much oxygen? 6 moles require 3. 1 mole requires 3 by 6. 2 moles require 3 by 6 into 2. 1 mole. Only 1 mole of oxygen is required by this much amount of water, and oxygen is 3 moles, more than what you require. So water is the fellow which will be consumed in totality. Little bit of Fe2S3 will be unreacted, little bit of oxygen will be unreacted. This is the limiting reactant. How much FeOH thrice will be obtained? Just concentrate on the limiting reactant. 6:4. 6 gives 4. Unitary method. 1 gives 4 by 6. And therefore 2 gives 4 by 6 into 2. 4 by 3. 4 by 3 moles of FeOH thrice will be formed. And in the vessel, you will have sulfur also, you will have Fe2S3 also, and you will have oxygen also. But there will be no water left in the vessel. Any questions? Let me know. Let's talk about another practical problem. When you want to react things with each other, then practically things are not pure. This reaction, for example, is taking place when all the 3 things are pure. Fe2S3 is pure, water is pure, oxygen is pure. But in reality, if you take some sample of Fe2S3, for example, or for any other reaction, say iron is reacting with somebody, and you have taken a sample of iron, then it will not be just iron. Some impurity is bound to be there. Nothing is 100% pure. But chemical reaction is about 100% purity. If iron reacts with somebody, it is iron only that can react with that thing in that particular manner. If some other impurity is present in that iron sample, then that impurity won't react. So some problems will be based on percentage purity. So suppose you are told that the iron you are using is 50 grams, or let's say 100 grams. Iron sample is 100 grams. Iron sample is 100 grams, but it is 40% impure or 60% pure. If it is 60% pure, then only 60 grams are meaningful for that particular reaction in which iron is going to react. Right? The impure part will not react for that particular reaction. Let's take a problem based on this. Sodium carbonate sample is 92% pure. That means sodium carbonate is 92%, 8% are impurities present in it. We are considering this reaction, and in this reaction, impurities will not participate. Suppose you want to prepare 1 gram of calcium carbonate via this reaction, then how many grams of sample should you use? How many grams of sample should you use? All right. Now, calculations based on reactions are done using moles. We always convert moles to grams later on, normally speaking. 1 gram calcium carbonate, mole-wise there is 1:1 ratio. 1:1 ratio for pure Na2CO3 and pure CaCO3. 1 mole is to 1 mole. So 1 gram CaCO3 means how many moles? One gram CaCO3 means how many moles? 1 upon?
Say 1 upon 100.
1 upon 100. 1 upon 100. 1 upon 100 moles. One upon 100 moles. So how many moles of sodium carbonate do you need?
So 1 upon 100 itself.
1 upon 100 itself. 1 upon 100. Now, if you need 1 upon 100 moles of sodium carbonate, pure it is. That means how many grams do you need of sodium carbonate multiplied by how much? Anybody?
So the 106.
106. Let's see. 23 into 2. 46. Carbonate is 60. 106. These many grams of pure Na2CO3. Sample is impure. So how much impure Na2CO3 you need? Considering the percentage purity is 92%, into 100 by 92.
Sir, could you please explain this step once again?
It's like this. Suppose I have got X grams of impure Na2CO3. No, let me make it pure. X grams of pure Na2CO3. But the sample is impure. Or I should say I need X gram of pure Na2CO3. I don't have pure Na2CO3. The sample that I have is impure. And its percentage purity is Y. So I need how many grams of the sample? It is basically math, not chemistry. Suppose I need Y grams of the sample. Then Y into whatever percentage divided by 100 will be X, and therefore Y will be X into 100 divided by percentage purity. Just simplify and see if you are getting 1.15 grams. 1.15 grams. So if you want something pure, then you will have to take more impure sample of it. That's very obvious, isn't it? I want 100 grams of pure iron. 100 grams of pure iron if I want. Then I will have to take more than 100 grams of impure iron. That will have 100 grams of pure iron, and rest will be the impurities. Another problem based on the same concept of percentage purity. Urea, NH2CO NH2. Some sample of urea was found to contain 42.5% nitrogen. Normally when we say 42.5% nitrogen or 60% iron, whatever, then these things are on mass basis. Generally they are on mass basis, gram, for example. So some sample of urea was found to have 42.5% nitrogen. Then what is the percentage purity of the sample itself? Of the urea sample itself, what is its percentage purity? Now, the problem here is that nitrogen percentage in urea is fixed and it is not 42.5%. And we can easily find out what is the nitrogen percentage in urea. You will see 2 atoms of nitrogen, 14 into 2, 28, and 28 plus 4 hydrogens is 4, 28 plus 4, carbon is 12, plus 12, oxygen is 16. So molecular mass is 28 plus 4 plus 12 plus 16. Only 28 is nitrogen. So percentage of nitrogen is 28 into 100 divided by that molecular mass. That's a fixed number. Nitrogen percentage in urea is a fixed number, no matter in which country you get it, no matter how you prepare urea. Everywhere it has to be that only, percentage of nitrogen. And when you calculate it, it should come out to be around 46.7%. But that is about 100% pure urea. But in reality, you don't get 100% purity. There is bound to be some impurity. It's a question of significant figures. 100.000000, that way it's not possible to get that much amount of purity. Now, 46.7% it should be for pure urea sample, percentage of nitrogen, but it is 42.5%. So is it not possible to tell the percentage purity of that sample?
So would it be 42.5 divided by 46.7 into 100?
Yes, that's how it should work. Linear. Any questions? Let me know. We are now ready to take bigger cases. Many times what you want to prepare is not obtained at one go, and you need to perform some sequence of chemical reactions. Let's say we are talking about preparing this polymer C2H4 coming N times. You know that C2H4 is called ethene. So this polymer is the well-known polythene polymer. So we are trying to prepare polythene. We start with calcium carbide. That's our primary raw material. Water is cheap, so let's concentrate on calcium carbide. We start with 10 kilograms of calcium carbide, and first we prepare ethene, and then in fact this is in first stage acetylene, ethine, and then ethine is converted to ethene by the addition reaction, and then this ethene is polymerized and we get polythene. N can be a very large number. A polymer has got large chain, very, very large chain. 10 grams of calcium carbide can get us how many kilograms of polythene? Assuming all ethene is converted to polythene, all of it. All ethene is converted to polythene. If all ethene is converted to polythene and there is no other thing which is getting added, then whatever is the mass of ethene, same should be the mass of polythene. So if question is asking 10 kg of calcium carbide can give how much weight of polythene, then the weight of polythene is same as the weight of ethene, because you are not adding something to it whose mass should be added, and there is no other reaction, side reaction taking place. We are ignoring all that. We are assuming all ethene is converted to polythene. So we just find the mass of ethene, and that will be the answer for the mass of polythene, right? And that should be fairly simple to do, because 1:1 and 1:1 relationship. That relationship is always in moles, never in grams. So 10 kg calcium carbide, can you convert it to moles? Calcium is 40, carbon is 12. So 40 plus 24, 64. 10,000 divided by 64 moles, 1:1. Same moles of acetylene or ethine, and 1:1. Same moles of ethene also. So these moles of ethene, moles multiplied by molar mass will be the mass in grams. Moles multiplied by the molar mass of ethene, 24 plus 4, 28 grams per mole is the molar mass. So when you calculate this thing, see if you are getting around 4.4 kg, around 4.4 kg. 4.4 kg of ethene is obtained and is fully converted to polythene. Any questions? Let me know. Let's take another problem. Again, based on some sequence. Again, it's polymer. Does anyone recognize this polymer? CF2, 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 CF2 n times. It's a very famous polymer, and you actually, I think, know it. You may not know that it has this formula, but you certainly should be knowing the name of it. Anybody?
Is it Teflon?
Teflon. It is Teflon. Now what we want is 1 kg of Teflon we want. So the question is, if we want 1 kg of Teflon, then how many kilograms of fluorine should be taken? How many kilograms of fluorine should be taken? That's the question. You should always work backwards in such problems. You know, kg of Teflon, you can easily convert that to moles. And this is the intermediate. Fluorine reacting with something gives you this intermediate. This intermediate is treated by this, and that's how you are getting this. They are all balanced reactions. You can check that if you want, make some random checking. See cobalt, how many particles? 4n particles. Here how many particles? 4n particles. And you can check fluorine if you want. Everywhere you will find it's balanced. 6 fluorine here, 6 fluorine here, it's all balanced. So we can find out moles of this fellow from 1 kg, and then this intermediate has how many moles? 4n times moles of this fellow. 4n is to 1. That's the ratio. So whatever moles we have got for this fellow, multiply those moles by 4n, and you will get the moles of COF3. Then whatever moles of COF3 you get, fluorine and that fellow, they have got 1:2 relationship. So whatever moles you get for COF3, half will be the moles of fluorine. Right? Half will be the moles of fluorine. And once you know the moles of fluorine, you can calculate the mass of fluorine also. So let's do it. 1 kg, 1000 grams. We want its moles, so its mass, molecular mass. 12 for carbon. Fluorine atom is 19. 19 into 2 is 38. So 12 plus 38. So polymer has one unit called monomer, and that monomer is repeated several times. So think of CF2 as a monomer, and one unit, that is one monomer, has mass of 50. 38 plus 12, 50, and that monomer is coming n times, so 50n is the molecular mass of this fellow. So you got moles of this fellow, and that is this much. That becomes 20 by n. That's a short number. 20 by n. 20 by n. Now, whatever moles of this, 4n times are the moles of this fellow. So multiply 20 by n by 4n into 4n. It's done here. For 4n into 20 by n. These will be the moles of this fellow, COF3. 80. 80 moles of COF3 will be there. 80 moles. So 80 moles are formed here, and the fluorine and this fellow 1:2. This is less, half times of 80. Half times of 80 is 40 moles. So 40 moles of fluorine. Any questions up to this point, let me know. Well then, from moles you can easily get grams. Fluorine atom 19, molecule 38, 40 moles, and 38 gram per mole is the molar mass. So 40 into 38 is how much? 40 into 38 is 1520 grams. 1.52 kg, around 1.5 kg. So if you take 1.5 kg of fluorine and other things are sufficient, COF2 is sufficient in quantity, and later on CH2N is sufficient in quantity, then you will be able to prepare 1 kg of Teflon. Any questions? Let me know. Very well. Now my question to you is, if enough quantity of COF2 is present, then how many moles is it? If enough quantity of COF2 is present, then how many moles of it? Minimum. We don't want to waste COF2 also, so don't take it in excess. The minimum moles of COF2 required to get 1 kg, right? That's what you have to tell. That's your assignment. We stop now.